Thanks a lot for both the invitation and the introduction. So today, since this is post-lunch for you guys, I thought I'd start with a very relaxed storytelling. So today I'd like to tell you a story with not many equations, so you don't have to worry too much about how the success of atomistic machine learning is pivoted on some key ingredients that reveal a very well understood way of learning things, and which can be extended to a more complicated targets, which we'll also see today. So before I jump into these N-centered or message passing based representations, I'd like to talk a bit about like a ML primer of how things are done, so you can better appreciate how all these representations and symmetries find their way in the realm of atomistic ML. So in this very I don't know, a slide that you might have seen very many times before. Generally, one is interested in building models for a specific property of interest, could be into atomic potentials, NMR shieldings, what have you. So you start with a bunch of structures, which I represent here by this cat A. And here, basically, you have information about the atomic species and their coordinates. And then many people, including myself, spend time on constructing these representations from the structure, which are then used as inputs to a model. So this model could be linear, could be kernel-based, could be neural network, whatever. So here, for example, I have a linear model. And so a model learns a set of weights, which when combined with your input, so this representation, reproduces to the best of its ability some reference calculations that you have performed for your structures. And then you use these learned weights on some other structures which your model has not seen before, and then you use this to predict the corresponding property. So far, so good. And there exists at the same time an alternative set of schemes which do not make this distinction between a representation construction and a modeling step. And instead, they form this end-to-end model. So they take your structure directly, you have a black box, and then you have a prediction. And so it's important to remember that there are these two set of schemes, which for a long time we thought that they were disconnected. And it's worth thinking about if they are really disconnected or if you can relate the two. So we'll see shortly if that can be done. So before I tell you about why so many people are interested and spend so much time in constructing these representation functions, I'll quickly give you a brief overview of how this is done, at least or how I've thought about it. So you start with this structure, for example, here you have some atomic positions and the species of the relevant atoms. So you start by assigning a localized function, could be a Gaussian, could be Dirac delta, anything. And then here, for each atom in your structure, you construct a localized environment around it. So in this environment, you're seeing other atoms in your structure, right? So for each central atom, you one by one enumerate all the neighbors present in your system. So since you're doing this for each pair of atoms in your structure, so for each central atom, you're identifying another neighboring atom, we would call this a pair density because it's literally telling you the position of a neighboring atom with respect to a central atom. And then what one does is you sum over all the pair densities in your environment and assign this function, which is called a neighbor density, to your central atom. So you have probably seen this before in multiple different forms. And the procedure that I quickly described to you in words entails some sort of mathematical operations that encode this neighbor density with some sort of symmetries. So identifying these relative positions, encode your representation with translational symmetry because you're now working with displacement vectors instead of absolute positions. And then considering the sum incorporates permutation symmetry in your structure. Now, these are usually for the rotationally symmetrized. And when we talk about rotational symmetries, you always see this NLM index popping up. So this is not surprising because spherical harmonics basically provide the most natural language to talk about rotations. So generally, this function that you have constructed here, the neighbor density, is projected on a spherical harmonic basis. And then you perform a rotational symmetrization over this neighbor density alone or over multiple copies of it, usually what is called taking a tensor product of multiple densities. And we'll see what this means shortly. So since this system that I propose to you right now is generally applicable to any sort of system, this would be called an atom-centered density correlation framework because you're working with atom-centered densities and you're considering correlations of them. And in short, this would be ACDC for all the rock fans in the audience today. So one wonders why one needs to go through such a complicated procedure that seems so involved. So that is an advantage. So for example, here I have 3 water molecules, which are rotated copies of each other. And now imagine that you're trying to build ML models for the energy of a water molecule. So to a rigid rotation in vacuum, the energy should not change of this water molecule. So basically, we are here trying to learn the same value for 3 different structures. And if we followed the procedure that I described before in this ACDC framework, what happens is that the intermediate function that you get is the same for all these 3 structures. So really, you're mapping these 3 structures which are related to each other by symmetry to one input. And then your model needs to learn this map from one input to one output. So you basically reduce the burden on your model to learn really what is equivalent, right? Because of the symmetries you inbuilt into your representation. And this neat framework is not just restricted to learning this invariant property of energy, but it can also be extended. I hope you can see my screen here because it's slightly hidden by Zoom on my own computer. What I want to say here is this neat framework can be applied to more complicated properties. So for example, here, I'm showing here a dipole moment vector of a water molecule that rotates as you rotate the structure. So this could be, for here I'm talking about dipoles, but could be any tensorial property. So this tensorial property is usually written in terms of spherical harmonics again, because again, these properties rotate with your structure and spherical harmonics provides the language of encoding this rotational behavior. So for a vector, we see that this is written as a spherical harmonic of order 1. So again, I have these 3 different input structures, which are rotated copies of each other. And now instead of mapping to one output, they map to 3 different outputs. Now these outputs are also related to each other by rotation. And so you start by building atom-centered densities again, just by the framework that I described to you before. And then you consider this additional function, right? So this additional function incorporates in your representation how this property rotates with your structure. And then you perform this rotational integration again. So here I created a model that rotates the same way as a property. So a spherical harmonic of order 1. And again, using one set of weights. So one set of weights, you map these 3 different structures to 3 different outputs. And this is in spirit of what is called a Wigner-Eckert theorem. If you don't know it, you don't need to worry about it, but basically, it just says that your rotational property can be decomposed in something that really rotates as you geometrically rotate your structure, and something that remains invariant. So here the weights are really invariant because you encoded the rotational behavior in your representation. So this I would like to think or motivate in terms of adding chili to your recipe of machine learning. So some people like chili because they want to think about equivariance. Some other people don't care so much about equivariance and they don't need chili in their recipes. And you can also tailor how much chili you add into your recipe to depending on your liking. And we'll see how this plays with other ingredients of machine learning. So one of the reasons why people like to also think in terms of representations is because it provides a complete linear and interpretable basis for your property of interest. So far, we are learning a property Y of a structure A, which we decomposed into atomic contributions. And because we decomposed our structure into local atomic contributions as well, we are mapping each atomic contribution to each atomic representation. And then you can, again, as physicists or as mathematicians, you can think of approximations. So how to represent an atomic contribution, you can think of pairwise contributions, triplets contributions, and so on. So to motivate this, I would present to you an analogy instead of presenting to you equations. So today I would invite you to think about this one person called Bob, whose energy we are trying to analyze during the day. So his energy, for example, depends on his interactions within his friend circle. So maybe Bob interacts with Jim, he interacts with Sally, he interacts with Alice. And so the sum of these pairwise interactions influences energy. So this pairwise interaction pops up naturally for atomic systems when you integrate over rotations one copy of your atom center density, because this really brings you information that is about pairwise distances. And now you can think about corrections to this contribution. So maybe Bob gets along individually well with Jim and Sally, but when the three of them are together, they fight a lot. So their energy changes. So you also need to incorporate for these two neighbor correlations. And then you again consider sums of these. So all energies of triplets. And again, you would get this naturally by integrating over two rotations or integrating over rotations of two copies of your density. And this you've probably heard of as soap power spectrum or power spectrum in general. And this is basically a two neighbor correlation. And then you can go on and on. So here we again now look at Bob's interaction with three of his neighbors, and we construct a three neighbor correlation. And this is something that you get by integrating over all rotations three copies of your density. So for a long time, it was considered hard to construct representations that capture higher neighbor correlations, because you need to integrate from scratch these, if you're considering n order contribution to your property, you need to integrate over n copies of your density, which is in general hard to do. So one of the things that was nice, not only just by the name of the framework, but I also think it's a very neat architecture, is that you can realize that this three neighbor contribution. So for example, in this case, you can consider this three neighbor contribution as recycling information about maybe Bob's interaction with Sally and Alice at the second order, and then considering Jim's influence on this two neighbor correlation. And mathematically, you can do this as well. And this is what you've described in this nice framework, because then basically it leads to a recursive way of computing higher order contributions from the lower order ones. So I won't bore you with the details, but I will leave you with a reference for it. But getting back to our story about spices and atoms, I like to collect all the ingredients that I have presented to you so far in this spice box, which you can basically find in all homes in the land that I come from. So I will now quickly summarize for you all the spices that we have accumulated in our spice box so far. So over the last decade, a number of representations have appeared. And this is summarized in this tree from a figure in this paper that looks a bit overwhelming when you first look at it, but it's only because there's been so much progress, but it all seems to be related to each other. So again, we are trying to represent in some way Cartesian coordinates of our structure, and we do so by incorporating different sort of symmetries to different extents. And that leads to this variety of representations that basically more or less telling you the same idea. And okay, again, at the same time, you have to remember that this alternative set of schemes which form the end-to-end models also exist on top of this framework. And these have been successful because of these ingredients which now fall within our spice box. So I talked a lot about symmetry, and that has played a major role in extending atomistic models to learning more complicated targets such as dipole moments or polarizabilities, in addition to just the interatomic potentials. There is this concept of locality and additivity, because we've been constructing our representation of a structure as sum of local contributions. And then there is this idea of completeness, because we are constructing this intermediate function that takes our structure to the input of our model. We'd like that distinct inputs be mapped to distinct outputs. Otherwise, we have lost the advantage of constructing this intermediate function in the first place. So One other ingredient that one is interested in is, so far we've been talking about atom-centered contributions, right? So what if our property is not atom-centered, but in general N-centered? And this is something that I talked to you about now. So over the last couple of years, also, there has been significant interest in building more general machine learning models for more fundamental quantum mechanical outputs, not just like for individual properties. So one of these is the effective single particle Hamiltonian matrix, which is in general indexed by two orbitals. So these two orbitals can be on the same atom center, or they can be in general on two different atomic centers. So we need a representation that treats on the same footing two different atoms. And one way of constructing this pair or two-center representation is by realizing that you have built this atomic representation. So you have a way of describing your atomic center. And you also have the way of tagging individual neighbors in your neighborhood. So you have this pair correlation as well. And so when you take tensor products of this, so when you combine this information about a pair density and an atom density, you get what is called an atom pair correlation. So again, going back to our analogy of people, so we have here Bob, whose local friend circle I've described again by one neighbor at a time. So again, you have to remember that you're summing over all neighbors one at a time. But for illustration purpose, I've just shown one. And then we have the special neighbor Sally. So for example, here you can say, think of the red atom as Bob and the blue atom as Sally. And then we'd now like to describe the environment of this couple. So Bob and Sally form a special pair or a couple whose environment we need to describe now, because we now need to describe a property related to this pair. So one way to do this is consider the influence on their relation by Bob's friends. So you can think of, how does Alice contribute to the pair relation of Bob and Sally? Or how does Jim contribute to this relationship? And then what you get is a two-center, one neighbor correlation, because you're looking at two centers and only considering one neighbor. So that was a bit of asymmetry, right, in this description that I just presented to you, because I chose to describe the pair environment by Bob's friends, but at the same time, I could have chosen Sally's friend to describe the pair environment. So there is this asymmetry, which is sometimes useful, because right now I'm able to distinguish which one is Bob and which one is Sally, because I told you that the red atom is Bob and the blue is Sally. But we'll see in the next slide when this is not possible to do. So going back to our example of the Hamiltonian matrix, you can decompose this in 3 blocks. So it's a bookkeeping nightmare, because you have to account for various different sort of symmetries that pop up when you're talking about Hamiltonians. The first being the very obvious Hermitian symmetry. And then you realize that you can decompose the Hamiltonian into blocks depending on where the two orbitals are centered. So you have, for example, the diagonal block, where both the orbitals are centered on one atom. So here, for example, both the atoms are centered on, both the orbitals are centered on the oxygen atom, sorry. And then you can have offsite matrix elements from different species. So here, for example, again, I'm able to tell you that one orbital is centered on oxygen, one orbital is centered on hydrogen. So for example, here, going back to our analogy of Bob and Sally, we are able to distinguish which one is Bob and which one is Sally, and which is the one I chose to describe the environment. But then comes offsite matrix elements, which correspond to orbitals centered on atoms of the same species. So here, for example, I have orbitals on both hydrogens, but they are two different atoms. So you have to account for the way you label hydrogen 1, hydrogen 2. And so this is what is called permutation equivariance in general. And this is something you'd need to encode in your representation. So we incorporate the representation of the S2 groups, because basically the symmetry of considering the symmetric contribution and the anti-symmetric contributions from two centers. And then what happens is very, very neat, because probably all the molecular chemists in the audience know this better than I do, is that all the point group symmetries of different molecules, they are from a subgroup of the permutation and rotation groups. So since your representation already accounts for the rotational and permutation symmetry, you get an output which automatically encodes the molecular orbital theory within it. So to illustrate this, here I created one random Hamiltonian matrix of a benzene molecule. So the matrix was literally filled with random values. So when I trained on this one matrix and tried to predict the same, the output is a bit absurd because, of course, the matrix elements were random. So, of course, the output is also random. But what happens now is because of the way this is predicted, it's predicted on the basis of an input which encodes the molecular orbital theory. You get from the output an eigenspectrum that automatically encodes the degenerate levels of benzene. So in benzene, and going back to the basic Huckel theory, which I know from undergrad, is that there are two sets of degenerate eigenvalues. And what happens now is that if you try to distort the benzene molecule, your eigenvalues, the degeneracy also breaks according to this distortion, which is called the Jahn-Teller effect. And your model already incorporates that without the extra effort of capturing this symmetry at all. So this is case in point, which is saying that, okay, all this effort of constructing representations that capture symmetry are actually helpful. And now I would like to go back and talk to you about this alternate class of models that I've already always been pointing to, which are the end-to-end models, and which do not really focus so much on constructing a representation. But one of the things that they rely on a lot is communication between different atomic centers. So this is usually thought of as message passing. And I'd like to now point out to you how our framework, this atom-centered density framework, can be generalized to incorporate message passing because of all the, because we have now all the ingredients that lead up to this point. So till now, I told you about constructing atom-centered features, which here in the language of message passing, I write as HI and HI1. And I also have a way of describing the connectivity between them through this pair correlation representation. So in a way, I have the ability to describe this pair of atoms and the connectivity between them. And in general, I can do this for n atoms in the environment, in some local cutoff. And so what I have the ability to do now is collect information on all these different centers, weighted by their displacement from the central atom, and collect this into what is called a message function that is invariant to how you consider the different atoms in your environment. And use this collected information about the neighbors to update my representation of the central atom in what is called an update phase of a message passing scheme. So what it basically does, you collect information from everything that happens around you and you use it to update your own information. And so again, to illustrate what is the difference between all the ACDC schemes I've been talking to you about so far, we have seen one neighbor correlations where we are considering Bob's interaction with one person at a time. Then we looked at two neighbor correlations where we now look at Bob's interaction with two of his neighbors and so on. Now, the equivalent scheme of in terms of message passing would be, again, we start with one neighbor correlation on Bob. So we have Bob and one of his neighbors. Then we choose a special center, Sally, to now describe a two-center correlation. And now this, in general, Sally can have her own environment, right? So I can choose to describe Sally's environment up to one neighbor, two neighbors, or so on. But in this scheme, I use the 1-1 scheme, which means that out of my two centers, I'm describing each of the centers with one neighbor. So I have information about two centers and two of their neighbors. And so in this figure that I show you here, Bob directly does not see Jim. So in the case of local atom-centered contributions, Bob would never see Jim. But in this message passing scheme, Sally acts as a gossip monger, so she brings out gossip about Jim to Bob. Okay, and you can do so. You do this for all the neighbors, so all different variations of Sally in your neighborhood, and so you use this to update the information on Bob now. And so an alternative, in one other alternative, what might happen is that Sally, you're looking at Sally, and the neighbor of Sally is now within the cutoff of Bob. So Bob now still knows about Jim. So does message passing really help us here? Because we already have information about Jim from our atom center on Bob. And it does help. And we'll see this on the next slide. So here, here is a random methane data set from this paper, which proved to be quite difficult to learn. So here, if I look at a carbon-centered model, so here I just look at models that are centered on carbon and look at three neighbor contribution. These saturate quite early, right? So it's attributed to the fact that carbon center models are not effective enough to describe the interaction between two hydrogens that happen a bit far away from the carbon atom, even though everything is within the cutoff of the carbon-centered environment. So you need a very high resolution to really see what's happening between two hydrogen atoms. So what happens if you center over all the atomic environments? You construct a representation that has information about all your atomic environments, and that helps resolve the problem that you weren't able to see two hydrogens before. And now, with this message passing scheme, a carbon-centered environment now is able to resolve what happens between two hydrogens that are far away. So really, message passing helped better resolution of your atomic environment. So that's one case in point about why message passing can be really helpful. Even if it really does not bring you long-range information, it helps you better resolve your atomic environment. And another way of looking at this is through what is called a global feature reconstruction error, which is described in this paper. So really what it's telling you, this GFI of psi prime, is telling you how much error you make in linearly writing psi prime as a linear combinations of psi. So this function here gives you a value close to 0 if you can really write psi prime as a function of psi, and a value close to 1 if they are really independent of each other. So in this figure here, you see that if I try to write this message passing representation as a function of my 3 neighbor correlation, I incur a higher error than if I do vice versa. That really sort of shows that I have somehow encoded more information in my message passing scheme, linearly speaking, of course, than just by spectrum, which are both ways of looking at three neighbors with respect to your central atom. And I would now like to conclude by really reuniting all the different things I talked to you about today. So I started with this tree, which showed you what sort of representations have been used over the last decade or so, and what sort of symmetry operations were used in describing this tree in itself. And then we built a whole tree of models on top of these representations, because these could be used as inputs to linear, kernel, or neural network-based models. And then even within this neural network modeling schemes, you have different sort of neural networks, which evolved sort of more or less independently, except for maybe these feature-based neural networks, which used as inputs these leaves from this tree. And there's another branch which evolved as message passing based neural networks. So now we have a way of basically relating all these branches of this purple tree with the original branch, with the original tree of representations through this message passing based representations. And of course, this field, which has evolved almost independently, has its own set of spices, if you will, because they make use of nonlinearities, of attention-based schemes, which once we are able to write these neural network models in terms of these message passing based schemes, we can identify and isolate what these different spices do in order to make their performance so wildly different in some cases. And so in conclusion, I present to you, even though I'm a fan of cooking from the heart and not following a recipe, I present to you some key ingredients that we have identified, and we have used these to unravel the different sort of approaches that have existed in machine learning for atomic systems. And now we have the possibility of borrowing schemes from these other trees and use them to extend our spice palette. And then really unravel all sorts of cooking out there. And now we have also now basically equipped ourselves with a kitchen so that we can go ahead and compete with all these dishes that are out there. So with that, it's been a great pleasure to talk to you here today. And I'd like to thank my collaborators and also leave you with some references where you can find the real equations that go behind all the stories that I've been telling you today. So thanks.